This is another result. This is not of a theoretical calculation, but this is an interesting little observation about nails, right? So a very simple physical piece. So lots of nails, they're not isometrically the same, right? They're not a simple scaling of each other, and they tend to actually get thinner as we make them longer. So there's a little argument for why this is. If you can see up in, is that a good idea? No, I should do that. Oh, maybe. Yeah. So these are nails, right? This is a slope of 2/3. This is their diameter and their length, right? So diameter is growing as length of the 2/3, so it's slower than sublinear. So, and this is slope 1, right? Again, on a log-log plot, it's 2/3. So it's growing sublinearly. So they're not getting as thick, right? So if you double the length, you don't double the diameter. You do something less than that. Interesting. I don't know what I've done there. Okay. So diameter is proportional to, you can figure this out from this. If you have this scaling, length times diameter squared is proportional to volume. That has to be true, right? That's not going to go away, right? That's the little cylinder things. Then this is the way they must fit together. So the diameter has to be proportional to mass to the 2/3, or volume to the 2/7, I should say, or volume to the 2/7. Length is going to go like volume to the 3/7. So this, right, this length to the power of 2/3, 2/3 of 3 is 2, so we get back to diameter. That's the right thing. And to get to our volume, we need diameter squared times length times a pi. It's fine, but it's a scaling story. Length, diameter squared times length. 2/7 plus 2/7 plus 3/7 is 7/7. So that's how that fits together. So it's a peculiar scaling, right? The 2/3 is sort of a funny thing, but then we've got out to sevenths here. This is a physics thing. Sevenths shouldn't be there, but they are. Okay, so nails lengthen faster than they broaden, and this is, we're making nails for a purpose, right? We want them to work. We need them to be longer for this particular thing, but we don't want to use too much material, right? That's a waste. We also don't want it to be hard to nail in, but we also don't want to make it too thin because it will break. So that's the argument that's used for this. You need to know something from engineering, which we're not going to derive, but there's a result from engineering on buckling, right? So at what point will a column buckle under load? And so that grows as d to the 4th divided by length squared. So let's look at this, right? So this is really cross-sectional area, d squared squared. So there's a strong piece for diameter. So, if you double the thickness, you get a factor of 16, right? 2 to the power of 4. If you double the length, then you get a 4, but it's dividing it, right? So you make it longer, then it's going to be more unstable. Fair enough. Lengthening makes it more unstable. Thickening it makes it more stable. But thickening gives you a really strong returns, right? Really strengthens it quickly. Then we have to put in some other pieces. So this is the idea, right? This is, you can argue about this, but we're driving this nail in, and there's a resistance to it that's from the material that's around its circumference. And we suggest that that's going to be proportional just to the diameter. Maybe it's just sort of at the front of the nail. So if these two things balance up, so that you want a nail that's not too thick, not too thin, right? Too thick means you're using too much material. It's a little harder to put in. Too thin means it'll buckle. So then we're going to have these, this matching up. And if you divide through by d, you get a d cubed, and put the L squared on the other side, and we've got this d is proportional to L to the 2/3. So a little bit of, magic, but you needed to know something quite substantial to get to that, of course. Okay. So it's a tour of these things. All right. So Galileo made this argument about buckling and so on. Euler talked about these things as well. Another smart person. Right. And this is actually a science paper by McMahon. And it's in 973. Let's get this one. This holds, some parts hold up, but it's a size and shape in biology. Big story, right? So there's the buckling thing in here. Tries to get at shapes of organisms with this terrible Minecraft kind of idea. But there's a suggestion in here that they grow allometrically, which doesn't seem to hold up from larger data sets. Anyway, okay, that's good. Let me go back to where I was. All right.